Hi, welcome to the Solar Neutrino Problem, Part 2. This is the second video in our two-part series on the Solar Neutrino Problem. In Part 1, we saw how the Solar Neutrino Problem arose in observations by the Homestake, GALLEX/GNO, and SAGE experiments. Here, we're going to talk about the solution to the Solar Neutrino Problem. In Part 1, we saw that there were multiple experiments that measured the flux of neutrinos from the Sun. The first experiment, Homestake, only saw about 1/3 as many neutrinos as were expected from solar models. The GALLEX/GNO and SAGE experiments saw about half as many neutrinos as were predicted. There were different classes of explanations proposed to solve the problem. Maybe the experiments have some unknown systematic error. Maybe we really don't have a good understanding of how the Sun works. Or maybe something exotic is going on. Nowadays, this is understood to be the first experimental evidence for neutrino masses. Back in those days, neutrino masses were exotic, so it turned out that the answer was, indeed, that something exotic was going on. So yes, now these observations are taken to be due to neutrinos having non-zero masses. But how was this conclusion reached? That's what we're going to talk about here. This will be an example of how a scientific hypothesis, in this case non-zero neutrino masses, was tested. Here we're just going to concentrate on comparing the hypothesis of neutrino masses against experimental error or a misunderstanding of the Sun. There were more exotic explanations put forward to explain the solar neutrino problem, but we're not going to cover them here. Okay, so here's an outline of what we're going to cover. You can find references to the relevant papers in the description below. We mostly covered the relevant neutrino interactions in Part 1, but we will give a brief review here. For a bit more detail, you might want to check out Part 1 again. We'll also briefly talk about how neutrino masses can fit into these results. Then we'll talk about the experiments Kamiokande, Super-Kamiokande, and SNO. Lastly, we will say just a few words about the greater context of these results. I should point out that, like in Part 1, we're going to concentrate only on the experimental results and how they fit together to first raise and then solve the solar neutrino problem. We're going to be very light on experimental details. Okay, so let's start with a very brief reminder of the relevant neutrino interactions. For a slightly longer description, check out Part 1. Okay, so first, the neutrinos can interact with the W boson and a charged lepton, where the charged leptons are the electron, muon, and tau. For example, this diagram could represent a W+ boson decaying into a positron and an electron neutrino. The type of neutrino indicates how it interacts with the W and a charged lepton. The electron neutrino interacts with an electron or positron, where a positron is the antiparticle of the electron. The muon neutrino interacts with a muon or antimuon, and the tau neutrino with a tau or anti-tau. A W can also interact with the quarks in a proton or neutron. Here we see a proton emit a W+, turning the proton into a neutron. The W then disintegrates into a positron and an electron neutrino. So this process, if energetically possible, turns a proton into a neutron, a positron, and an electron neutrino. Processes like this lead to neutrino production in the Sun. In principle, one could write down this diagram using an anti-muon and muon neutrino, or an anti-tau and a tau neutrino. But nuclear processes have energies of order MeV. This isn't enough energy to produce a muon or a tau. So, since these reactions can't make a mu plus or tau plus, they can't make muon or tau neutrinos. So for all practical purposes, neutrinos made in the sun are all electron flavor. Okay, next we also need to know that neutrinos can interact with the Z boson. Here we show a diagram that can represent a Z decaying into an electron neutrino and an electron antineutrino. It can also decay into a muon-flavored neutrino-antineutrino pair or a tau-flavored neutrino-antineutrino pair. Like the W, the Z can also interact with other particles, like the electron. This can allow a neutrino to scatter off of an electron. The Z can also interact with quarks. This means that a Z can interact with a proton or a neutron. This allows a neutrino to scatter off of a proton or neutron. These interactions will be important when we look at Kamiokande, Super-Kamiokande, and snow. Okay, now let's briefly revisit the role of neutrino masses in the solar neutrino problem. So we saw that because the energies of nuclear reactions are of order MeV, only electron-type neutrinos, nu-e, are made in the sun. And we saw in part 1 that Homestake, GALLEX/GNO, and SAGE were only able to detect nu-e, not nu-mu or nu-tau. This is because those latter experiments utilized the process where a neutrino impinges on a neutron, changing it into a proton and producing an electron. While a similar diagram can be drawn with a muon neutrino and a muon, or a tau neutrino and a tau, solar neutrinos have energies of order MeV, which is not enough to make a muon or tau. So, solar muon or tau neutrinos, if they exist, would not be energetic enough to interact through this process. And that means that these experiments would not be able to see muon or tau neutrinos. So, to sum up, nuclear processes in the sun produce only nu-e, that's electron-flavored neutrinos, and Homestake, GALLEX/GNO, and SAGE were able to see only nu-e. So, what's the problem? The problem is that if neutrinos have masses, and those masses aren't all the same, then neutrinos can change flavor. If neutrinos changed flavor, then electron-type neutrinos produced in the sun may arrive at Earth as muon or tau flavored instead of electron flavored. Then they would have been invisible to the early neutrino experiments. So, how to test the mass hypothesis? If we have experiments that can see muon and tau neutrinos, in addition to electron neutrinos, the total neutrino flux from the sun should be compatible with that expected by solar models. Enter the Kamiokande, Super-Kamiokande, and Sudbury Neutrino Observatory experiments. Okay, let's start with Kamiokande and Super-Kamiokande. The Kamiokande experiment ran from 1983 until 1995. It used as a neutrino target 2,140 tons of water. Its successor, Super-Kamiokande, started in 1996 and uses 50,000 tons of water. Both of these experiments were situated in the Kamiokande mine in Japan. Both of these experiments look for neutrino interactions in water. Because Super-K had much more precise results, we're going to mostly look at that. If you want more information on these experiments, you might want to check out a couple of videos that are already on this channel. One is about the observation of neutrinos from supernova 1987A, and the other is about proton decay. Links are given in the description below. Okay, so Kamiokande and Super-Kamiokande looked for scattering of neutrinos on electrons. A solar neutrino can hit an electron in the water, giving the electron a kick. Light from the scattered electron is detected. This can happen if the incident neutrino exchanges a W boson with the electron in the detector. So we can read this diagram from left to right. An electron neutrino, at the bottom of the diagram, comes in and exchanges a W boson with an electron in the detector. This electron is at the top of the diagram. The neutrino turns into an electron, and the electron that was in the detector is converted into an electron neutrino. The electron that is created can emit light that is detected by the experiment. As we've said before, solar neutrinos can have enough energy to create an electron, but not a muon or tau. So any solar muon or tau neutrinos entering the detector cannot participate in an analogous process. Only electron-flavored neutrinos can. This is a lot like what we saw with Homestake, GALLEX/GNO, and SAGE. With this process, you can't detect solar muon or tau neutrinos. But there is also a second process. An incoming neutrino can exchange a Z boson with an electron in the water. Here, the charged lepton in the final state is always an electron and never a muon or tau, regardless of the flavor of the neutrino that entered the detector. So there aren't any issues with needing energy to produce a muon or tau, and all three flavors of neutrinos can participate in this process. Okay, let's look at those two diagrams again. Through the first process, you can only detect electron-flavored neutrinos. Through the second, you can detect any flavor of neutrino. Kamiokande and Super-K can see the resulting electrons from both of these processes. But for a given interaction, you don't know which process contributed. Because electron neutrinos can interact through either diagram, the cross-section for an electron neutrino to interact in the detector is about 6 times that for a muon or tau neutrino. This means that a muon or tau neutrino, if it enters the detector, is only about 1/6 as likely to interact as an electron neutrino of the same energy. This means that Kamiokande and Super-K could see muon and tau neutrinos, but not as well as they could see electron neutrinos. Okay, so let's look at their results. Both Kamiokande and Super-K saw a deficit of neutrinos compared to what was expected from solar models. We'll look at Super-K as they had the more precise results. They specifically looked at the boron-8 neutrino flux, which is from the process in the Sun where boron-8 is converted into beryllium-8, a positron, and an electron neutrino. The flux they reported was 2.32 times 10 to the 6 neutrinos per square centimeter per second, with an error bar of a few percent. This was about 45% of the flux expected by solar models. So just like in the previous experiments, they saw a deficit of solar neutrinos. We need to note at this point that Super-K's result is under the assumption that all solar neutrinos are electron flavored. Muon and tau neutrinos are less likely to interact in the detector. So if some of the solar neutrinos transformed into muon or tau flavor, they would contribute to the result, but at a rate approximately 1/6 as large as Super-K assumes. So transformation of solar neutrinos into muon or tau flavor would cause Super-K to report a deficit. Okay, now let's talk about snow. The Sudbury Neutrino Observatory operated from 1999 to 2006 in a mine near Sudbury, Canada. Their detector contained 1,000 tons of heavy water, denoted D2O. Heavy water is like water, except that the hydrogen atoms in water are replaced with deuterium atoms, which have a proton and a neutron in the nucleus, instead of just a proton like hydrogen has. And like Super-K, snow reported the boron-8 solar neutrino flux. Snow looked at 3 possible interactions of neutrinos in their detector. The first was neutrino scattering on electrons, the same as Super-K did. The other 2 were new. Let's start with their results for the scattering of neutrinos on electrons, as we're already a little familiar with that. Snow got a result of 2.39 times 10 to the 6 neutrinos per square centimeter per second, with an error bar of around 15%. This was in excellent agreement with Super-K's more precise result. So there was no indication from Snow that there was anything wrong with Super-K's result. In what follows, we'll use Super-K's as it is more precise. Okay, next let's look at the process where a neutrino, and specifically an electron neutrino, impinges on a deuteron, producing 2 protons and an electron. Again, a deuteron is a system which contains a proton and a neutron, so the neutron in the deuteron is being converted into a proton, and an electron is being emitted. This is the process nu-E neutron goes to proton-electron. We saw this same interaction in part 1. This same interaction, where an electron neutrino and a neutron convert into a proton and an electron, was used in the early neutrino experiments that discovered the solar neutrino problem. And again, just like in those experiments, solar neutrinos don't have enough energy to make a muon or a tau, so only electron neutrinos can be seen this way. But this means that, with this process, Snow could measure the flux of solar electron neutrinos without contamination from muon or tau neutrinos. So, using this process, they measured the boron-8 flux. They got 1.75 times 10 to the 6 neutrinos per centimeter squared per second, with the error bar shown. Let's compare that with the Super-K result. So Snow's result measures the flux of electron neutrinos, while Super-K's measures the flux of electron neutrinos plus approximately 1/6 of the muon and tau neutrinos. We can compare these numbers and see that there is a statistically significant difference between the two. So it appears that there are some muon and tau neutrinos in the mix. Furthermore, we can eyeball this to get an idea of the total neutrino flux. Both of these results are in terms of 10 to the 6 neutrinos per square centimeter per second. The difference between the numbers out front, that is the numbers 1.75 and 2.32, is about 0.6. As Super-K measures the electron neutrino flux plus about 1/6 of the muon and tau neutrino flux, we can take this difference of 0.6 to correspond roughly to 1/6 of the muon and tau neutrino fluxes. That would give a tau and muon neutrino flux of around 3.6 times 10 to the 6th per centimeter squared per second. If that holds, then the total neutrino flux would be that plus Snow's electron neutrino result. So we should expect the total neutrino flux to be something like 5.4 times 10 to the 6th per centimeter squared per second. We'll see shortly that this isn't too far off. Okay, so we've already seen a hint that muon and tau neutrinos are coming from the sun. But we still need to look at one more result from Snow. They also looked at the process where a neutrino hits a deuteron and breaks it up into its constituent proton and neutron. So here's a diagram showing how that can happen. A solar neutrino coming in from the left exchanges a Z with a proton. The neutrino thus scatters off of the proton, giving the proton a kick that breaks it out of the nucleus. The same thing can happen if a neutrino scatters off of a neutron. This process doesn't produce any charged leptons. The neutrino stays a neutrino. Since we don't need the energy to produce a charged lepton, all flavors of neutrinos can participate. Thus, this process measures the total flux of electron, muon, and tau neutrinos. Again, Snow reported the boron 8 flux. In the same units as before, they got a result of 5.09, with an error bar of a little over 10%. Let's compare the three results. Okay, so here are the three results, all in the same units as before. At the top, we have a result from Snow that measures the electron neutrino flux. In the middle, we have a result from Super-K that measures the electron neutrino flux plus part of the muon and tau neutrino fluxes. And at the bottom, we have a result from Snow that measures the total neutrino flux of all three flavors. By comparing the top and bottom numbers, we can see that the electron flux is only a smallish component of the total. Also, we can see that the guess we got for the total neutrino flux by eyeballing the first two results was not that far off. We said 5.4, and it's actually 5.09. So a large component of the solar neutrino flux appears to be muon and tau neutrinos. Furthermore, Snow's result for the total solar boron 8 neutrino flux was in agreement with the predictions of solar models. The missing neutrinos had been found. So, after Super-K and Snow, it was clear that neutrinos were changing flavor. Previous experiments, which could only see electron neutrinos, had been unable to see most of the flux. So we said at the beginning that there were three classes of possible explanations for the solar neutrino problem. They were experimental error, a poor misunderstanding of the sun, or something exotic going on. It turned out to be the last of these. Okay, I want to finish up by just giving a little bit of context for how these experiments fit into a bigger picture. So this was just the beginning of the story on neutrino masses. I don't want to give the impression that the solar neutrino problem was solved and physicists concluded that neutrinos had masses and that's all there is to it. So I should mention that Super-K and Snow also presented further analyses in these papers that I didn't discuss here. They also went on to publish many more results. And additionally, there have been many neutrino experiments since then. These results have been complemented by atmospheric, reactor, and accelerator neutrino experiments. The neutrino masses and mixing parameters are being systematically nailed down, and work is still ongoing.